So this residual stress is very beneficial. How do we get it into a ceramic material? There are three common methods of doing that. Uh, Two of them are still commonly used today. The third one has fallen out of use in dentistry. The two methods that are still commonly used, the first one is thermal tempering by using different ceramic materials and laminating them together into a multi-layered object. And you choose materials that have different CTEs, coefficients of thermal expansion. So that means when processing these materials, we heat them up and cool them down, they will change the amount that they will expand upon heating and the amount they will contract upon cooling is different. And the other method is by rapidly cooling a single ceramic material to room temperature after we process it in a furnace. And in that case, because ceramic materials have low thermal conductivity, the surface of the ceramic behaves as if it's a layer of a different material than the interior. Less common is the chemical tempering. The reason that one is not favored is that it creates a very thin compressive surface on the outside, and it's easy for subsequent damage to penetrate that and get into the interior. Okay, so if we layer ceramics together, some graphics to help you visualize what's going on there. We have, in this example, a ceramic object that has two layers, two different types of ceramics making it up. And on the inside, we have a material with a very high coefficient of thermal expansion. And the surface, the outside surface, is a different ceramic material that has a slightly lower coefficient of thermal expansion. These are being processed in a furnace. They're being melted or fused together. And then we take them out of the furnace and cool them down to room temperature. And they're going to shrink. Both of them will shrink somewhat. The one with the high coefficient of thermal expansion will shrink more than the one with the low coefficient of thermal expansion if they are not bonded to each other. But since they're bonded to each other, they have to shrink by the same amount. There needs to be a compromise between the two of them. And so they will shrink down, cool down to a intermediate size, and the one that wanted to shrink more, the one on the interior with the high coefficient of thermal expansion, is being stretched. It would like to be smaller than it is. So it has a tensile residual force placed in it. And the one that did not want to shrink as much has a low coefficient of thermal expansion. It is being compressed by the high CTE layer to be smaller than it wants to be. And so it has a compressive residual stress that squeezes cracks closed on the surface. I mentioned that the surface is slightly lower in coefficient of thermal expansion. It's important that it not be much lower. About 5% is the limit. We can make the material stronger and stronger up to the point where there's a 5% difference. If we go beyond this, then we crack the surface material and develop what looks like the crackle glaze effect that you see in many traditional Asian vases made of ceramic. We don't want that on the surface of our dental restorations. And then we have an animation down here that I will save and use for our discussions later in class. Okay, I mentioned that another method of doing this without using more than one material is to rapidly cool a single material. The reason that we can do that is shown here by a comparison of thermal diffusivity of various materials, and we see that ceramics, porcelain in this example, have a very low thermal diffusivity as far as materials go. So what that means is that as the surface, as the material is taken from the furnace and put in a room, which is room temperature, The heat from the surface will leave and go into the room, and the heat from the interior of the ceramic will fail to diffuse rapidly to the surface. And so the surface will become cool quite quickly, and it will take a long time for the interior to cool. And because of that, we can do neat demonstrations like the one done with this piece of a space shuttle tile, where you can place it in a very hot furnace and get the entire tile material heated so high that it glows orange, and then remove it from the furnace using a pair of tongs. Set it out at room temperature for a few seconds, and the edges and corners of the cube will lose their heat to the air in the room and become cool enough to touch, and the heat in the interior of the object will continue, causing it to glow. But because this particular type of ceramic has such a low thermal diffusivity, the heat in the interior can't make it to the surface to warm it up again, and it remains close to room temperature on the surface. Okay, so how does that work with how do we conduct the rapid cooling of a single type of ceramic? Imagine that the single composition of ceramic is in the furnace. It's hot everywhere, and we remove it and we place it in room temperature air there on the surface, and the heat leaves and goes into the air. However, because of the poor thermal diffusivity of the ceramic, the heat here in the interior fails to come to the surface and replace the heat that was lost. The surface cools below the glass transition temperature, Tg, at which it becomes a rigid material, and then the interior slowly cools over time and contracts, but since the outer surface is already rigid, the outer surface becomes compressed when the interior is contracting. And so that's another way of developing residual stress on the surface. The third method that's not popular anymore, I'll just briefly explain the mechanics to you. Chemical tempering instead of thermal tempering. It's also known as ion exchange or ion stuffing. The reason that we call it stuffing is that we start with a ceramic that has small ions in it, like this sodium ion, and we put it in a hot salt solution that contains larger ions, like this potassium ion. And some of the sodium ions leach out over time because of the concentration gradient between the ceramic and the solution, and they are replaced in some part by the potassium ions, which have to squeeze into that small space, and that induces a very thin but highly compressive surface layer, making a ceramic that is very, very strong. But if you introduce any type of crack into the object at all, will penetrate that compressive surface layer and get into the tensile stress in the interior and cause rapid propagation of that crack through the material, breaking the structure. Now, the tempering sounds like a wonderful method, but unfortunately we can't use it on all materials. It can only be used on materials that have a glass phase in them. And that includes glasses, which are all glass phase, porcelains, which as we discussed can be glass with crystals embedded in them, and glass ceramics, which is also glass with ceramic crystals embedded in them, which are produced by a different method that we'll go over later. So tempering is not eligible for polycrystalline ceramics, most notably the two that are currently used in dentistry, alumina and zirconia. And this is unfortunate because these are the strongest materials that we currently have available, and we can't use tempering to make them even stronger. So we had one last strategy available to use for increasing the strength and lifetime of ceramic components, and that was to place crystalline obstacles in the microstructure to help impede the growth of cracks. I'm illustrating that here with some electron microscope photographs of a material I created for my PhD research. And notice the year is 1998. I bet you all thought I was much older than that, but actually I didn't finish graduate school until close to the 2000s. And we can see here this plate shape crystal with a glass matrix around it, and the crack is going through the glass matrix. At lower magnification you can see lots of these plate-shaped crystals in the material. They don't look plate-shaped, many of them, because they're being cut in cross-section here. And you see how they're deflecting this crack as it grows through the material, and in some cases they even cause it to split and grow into multiple cracks that take more energy to go through the material and become larger. And this can increase the strength of a material by up to 3 times by increasing its fracture toughness. The effect depends on how close together the crystalline obstacles are. So how much a crack has to twist and bend to get through the microstructure, in other words. And that has to do with not only how much of the material is crystalline, the volume fraction of particles, but also the shape of the particles has a lot to do with it. Rods are more effective than discs, and discs are more effective than spheres. And if you have a similar type of shape, a larger aspect ratio is more effective. And just to remind you, the aspect ratio is the length of an object divided by its width. So there's an object with a high aspect ratio, and there's an object with a low aspect ratio. So, all right, low aspect ratio. And here are some examples of dental products currently on the market. We have rods reinforcing several types of materials there, and the weaker, older dental ceramic materials are reinforced with roughly spherical particles. And the crystals not only impede the growth of cracks, but they can be stiffer than the glass matrix that's surrounding them, and so they can take on some of that load and decrease the amount of stress that the glass matrix feels, and increase the strength of the material that way. However, putting a crystal inside of a glass material introduces grain boundaries, which can serve as flaws, places for new cracks to develop. And so you're actually causing a flaw where there wasn't one before. And that's why if we introduce only a little bit of crystals in the material, we actually see a small decrease in the strength. And then as we begin to increase the amount of crystals that are present, the stiffness of them has more of a benefit than their presence has detriment to the strength of the material, and we end up with a stronger material, especially in the case where we have very small crystals, and so their addition doesn't serve to create large flaws in the material. Here's some microstructures that can be seen in electron microscope for actual ceramics used currently in dentistry. And S in these photos represents strength of the material on average, and K1C is the fracture toughness of the material. And when the crystals are nano-sized and there's not many of them, they don't have much of an effect. This 90 megapascal strength is similar to what we would see for a glass without any crystal reinforcement. Even up to 20% of lucite, those roughly spherical particles, doesn't have much of a strengthening effect. It would be common to find a glass without crystals that had a strength of 100 megapascals. Then as we begin to add more lucite, more crystalline obstacles up to 35%, we see that the fracture toughness begins to increase slightly, strength is increasing slightly. If we go to a much higher amount of crystals, crystals are much closer together, 70%, and we've gone to a type of crystal that has more effect. These are rod-shaped crystals. Then we see the strength jumps up to almost 4 times what it was for the 35% lucite, and fracture toughness is almost 3 times higher. Now we have different methods of making the same material. We have 70% lithium disilicate in both that photo and that photo. The microstructures look different, and you notice the strength and fracture toughness are a little bit different. It's because melting and pressing the material into a mold results in a higher aspect ratio for the crystalline rods than the method where we use CAD/CAM to mill or machine the object into shape without heating it to become viscous and making it flow. And then we have the case here of 75%, so increasing 5% more the crystallinity and shifting to a different type of crystal. We see the strength jumps from 360 all the way up to 600. So why the big change for just a 5% increase in crystallinity? It's because the crystals in this case are actually touching each other, and if we look in 3 dimensions, we will see there's a continuous network of crystals throughout the entirety of the object. And so now the crystals have become the continuous phase, and the glass is just filling the space, the pores between them. In most of material science, we find that whichever phase is the continuous phase in the structure is very important. That phase, even if there's not much of it, the continuous phase will dominate the properties of the material quite often. This is another material that is mostly crystalline and has continuous crystals in it and glass filling in between. And then we go to our polycrystalline materials, the last 2 photos here, which are essentially 100% crystalline with negligible glass phase present, and those are quite strong and tough. So in summary, we have 3 strategies for improving the mechanical reliability of ceramics. We can reduce their flaws by polishing them or by fabricating them in a careful way so that we don't introduce flaws needlessly. That makes them stronger on average, and it has very little effect on decreasing the variability though, because although they start off very strong, they are subject to future damage. The second strategy is to increase the toughness of the material by modifying its microstructure with crystalline obstacles to crack growth. This not only improves the average strength, but it greatly decreases the variability in strength, because if we introduce a new flaw, then the material will be resistant to the growth of that flaw, just like it was resistant to any flaws that pre-existed use in the patient. And the third strategy is by tempering to produce a compressive surface stress in the material, and that improves the average strength and greatly improves the variability in strength. It is subject to future damage, but only if that future damage is very severe and penetrates the compressive surface layer. Unfortunately, tempering can't be used on all materials, only on materials that contain a glassy phase somewhere in the microstructure. So glassine materials can take advantage of all three of these strategies, but polycrystalline materials can take advantage of only the first two strategies. And just to remind you, your textbook contains an alternate description of some of this information. I'm showing you the page numbers that occurs on here. And if you have any questions after reviewing this lecture and reading the textbook, definitely please ask me those questions in class. And again, feel free, if you need to make an appointment to meet with me later in my office.